Yes. Well, yesterday we discussed the deterministic part of an earthquake, and there are two length scales, and one is space, the other one is time. So if we have different scales, you can make very deterministic forecast or deterministic prediction. And that part is sort of more standard physical problem, and as long as you know the physics, you can do very well. And there is some regularity and predictable. Uncertainties are still very hard to quantify. However, as I discussed, this is a natural process, and there are many non-deterministic elements. And the interaction between many elements in a large system can cause a very chaotic system. And it's very difficult to make deterministic forecast or deterministic prediction. This is not only earthquake. This applies to almost all natural processes. But in case of earthquake, we are dealing with two very different time scales. Geological process is a long-term process, but we are mainly interested in very short-term process like an earthquake. That's why this effect of non-deterministic process can become very serious. But in this case, even if we can't make a deterministic prediction of individual event, we can make some forecast regarding the overall behavior in terms of magnitude-frequency relationship. And so in other words, we can predict it only in a statistical sense. So in terms of time series, in case of deterministic, we have this one. In case of non-deterministic system, we have this one. And unfortunately, all natural processes have this element. So to some extent, we can predict this overall character, but we are not really, well, we are sometimes interested in the long-term process, but we are mainly interested in the short-term process here. That's why the earthquake problem is very difficult in terms of social implication. So this is basically what we discussed yesterday. So then the question is, given the non-deterministic character of earthquake process, and then diversity of earthquakes we discussed, what can we do? That's what I want to discuss. And I put more or less arbitrarily 4 subjects here. But of course, this is not completely comprehensive. Basically, I just picked those 4 topics. And the first one is really very well known. And I don't want to dwell on this for a long time. Improved engineering practice. This is very obviously important. And great credit should be given to engineers who really developed good engineering practice, which have helped a great deal in reducing seismic hazard. And from a seismology point, we need to characterize earthquakes. And of course, with advent of tomography and broadband seismology, GPS and everything, now we can really characterize earthquakes very quantitatively. That is a significant advance for the last decade or 2 decades. And also by using characteristics of earthquakes and tomographic knowledge, we can estimate strong ground motion. This science has progressed a great deal. So I will just touch on this almost, but this is already very well understood. So I'm not going to discuss too much about it, except saying that we have made good progress and we have to continue to make progress. The second, as I discussed, there is a tremendous diversity in earthquakes in terms of source spectrum, and we discussed tsunami earthquakes and intraplate earthquakes, but I want to go into more detail. And number 3 is recognition and understanding of outliers. We can understand the average process reasonably well by characterization of earthquakes. However, we do see outliers. Very often, we see very strange results, strong ground motion, and very narrow S-wave pulse, for example, that can cause significant damage. And we need to understand it, and we want to understand it physically, and so on. And lastly, no matter how we did it, earthquake happening is very abrupt. We can't really predict exactly when the event is going to happen. So to deal with that, early warning system is very important. So I want to discuss those. Okay, so as I said, I'm really not going to talk about this one. Improved engineering practice, characterization of earthquakes, and estimation of strong ground motion. In these areas, with the advent of data, computer, and theory, advances have been made. And with better characterization of earthquakes, with broadband seismology, significant progress has been made. So it can only get better. We have to continue to do good work in basic research, and also its quantitative application. Okay, so the second thing is the diversity of earthquakes. To some extent, this has been recognized for a long time, but now recently we can discuss this diversity in terms of quantitative source spectrum. So by doing that, we can perhaps come up with better way to deal with earthquake hazard. And in the past, earthquake magnitude is the only really quantitative parameter for quantifying earthquake. But as I discussed yesterday, it was far from sufficient. Earthquake magnitude was determined only at one single frequency. And we need to really understand earthquake characteristics of a very broad frequency band. So magnitude is not the only parameter. We need to look at the entire spectrum. This is the whole idea of diversity. Well, yesterday I showed a similar diagram, but I said only the right-hand side could be determined with all the seismic instruments, and only up to nearly maybe 20, 30 years, that was the case. But with the advent of modern broadband seismology and even geodesy toward that end, now we can cover the entire frequency band from 1 hertz to 1,000 seconds or even longer. This is 1 second, this is about 1,000 seconds for all earthquakes from 5.5 to magnitude 9.5. There is no saturation, so we have a very wide dynamic range of the instruments. So we can cover this entire range. This range is relevant for tsunami at long period. It's relevant to tall building around 10 seconds to 1 second. It's relevant to ordinary structures around 1 hertz. And then very high frequency, it's relevant for PowerPoint program. So in a way, we now have a tool to understand the seismic source spectrum or moment rate spectrum over the entire frequency band. Then the next thing is to look at this one for different earthquakes and understand how they look like and think about what we can do. Well, the way we handle this is this. This is the same figure from 1 second to 1,000 seconds. And this blue curve is the observed source spectrum using broadband seismology around here and sometimes long period seismology and geodetic data. So as I said, we now can cover this entire range from 1 hertz to 1,000 seconds. So this is observation. We need to sort of look at this in the context of some reference, whether it's bad or it's good. We need to know some reference. So we use this reference spectrum. This really doesn't matter. This is a spectrum of a reference event with the same moment. Moment means the size of the spectrum at a very long period. So we match red and blue at long period and draw it and see how observed spectrum compares with the reference spectrum. For example, if the blue spectrum is above red spectrum, we say this event is enhanced at high frequency. In other words, strong shaking. If this is below red one, down here, for example, we say it's a slow earthquake. It doesn't have high frequency. However, long period size is normal. Or if you turn around, if you use high frequency as a standard, then that kind of event may have enhanced long period, the slow earthquake. So even if there is no shaking, the ground motion can be, ground deformation can be very large. So this reference spectrum is very useful to understand the observed spectrum in terms of its character, whether it's a strong shaking event, or whether it's a silent event, or whether it is a slow earthquake. Well, then we can determine this for all the big events, and for the last 10 years or so, we have been, whenever there was a big earthquake, we determined for individual earthquake. This is 2011 Tohoku earthquake, and rather interestingly, this shape is very similar to this reference spectrum. However, it is a rather unusual event, but there are two effects cancel each other. So as a result, the spectrum looks like rather standard. We'll talk about later. And 2004 Sumatran earthquake, this has some deficiency over here. And the Chile, this is 2010 Maui, has sort of the same character. But this is a somewhat common shape for all these megathrust events. Okay, in the middle here, we call tsunami earthquakes. Tsunami earthquakes are domain A earthquake, which happen near the trench. And normally, those events have relatively slow motion. For that reason, high frequency spectrum is deficient here. All of them, 1990 for Java, 1992 Nicaragua, 2010 Mentawai, all of them, compared with long period, high frequency is quite deficient. Seismology, we use log scale, so it doesn't look much different, but in linear scale, it's a big difference. In this case, it's almost on the order of magnitude. So people really didn't feel this event because it's so weak at a short period. And the event I showed you yesterday, 1896 Sanriku event, of course, we didn't have this kind of data, but from the macroseismic observation, it's almost certain that it was something like this one. People didn't feel it because high frequency amplitude was very low, but long period amplitude was very high, and the tsunami triggered by that earthquake was among the largest in Japanese history. And this Java event is a bit strange. It's deficient over here, but high frequency, it's comparable. We have noticed this one very recently. So in a way, we call all of them tsunami earthquake. It turned out this is a slightly different character. I don't want to discuss in too much detail. And the bottom events here are what we call intraplate events. This is 2007 Kurile Island, and this one is 2009 Samoa Island, Philippines, and Miyagi-Oki. I showed you this aftershock of the 2011 Tohoku earthquake. For example, in this case, high frequency spectrum is very large compared with long period. And this aftershock here is very high frequency. This is really very high frequency. At even higher frequency, it's really an order of magnitude bigger than the reference spectrum. So this has very strong shaking. So earthquakes are very different in terms of source spectrum. So we have to use different strategy for hazard mitigation purposes. So this diversity is really very important to understand. Okay, so we first look at the domain A tsunami earthquake here. These events happen right here in the very shallow depths from almost 0 to maybe 10 to 15. This name, tsunami earthquake, is different from tsunami-genic earthquake. Traditionally, any earthquake that generates tsunami are called tsunami-genic earthquake. And tsunami earthquake means subset of it. Those events do not have strong shaking, but only large tsunami. That's why they are called tsunami earthquake, and domain A here. And some of them may have a slip over domain B2, but at least tsunami earthquakes have a slip over here. Okay, going back to the previous slides, these are the tsunami earthquakes, and it's very obvious that spectrum is deficient at high frequency. Or if you match at high frequency, for given shaking, long period amplitude will be very large. So this is a very troublesome event, because in case of large tsunami, in a way, usually most earthquakes are something like this one. In this case, people feel it, and that's a natural warning, so that people who have experience, when they felt strong shaking, they started moving higher area to avoid the tsunami. But in case of tsunami earthquakes, since shaking was so weak, whenever they felt it, they usually didn't pay much attention to it. And then 30 to 1 hour later, big tsunami came. And so this is a very troublesome event. And also for tsunami warning purposes, it's very obvious that you have to watch a long period part of the spectrum, because if you monitor only high frequency like here, it won't help, because you can't tell how big it is at a long period. And unfortunately, most tsunami warning system up until a few years ago, was rather strange, however, up until a few years ago, JMA, for example, were using only 20-second wave around here for tsunami warning purposes. So it's very easy to miss the real big tsunami earthquake, because if you look at here, it's a small earthquake, but tsunami can be very large. It's so obvious that much longer period should have been used. And this has been recognized for the past 20 years. And the instrumentation became available, and technology or methodology became available, but somehow it wasn't implemented at the time of the Tohoku earthquake. They were experimenting on it, but they never implemented it. So it was very unfortunate. So if that was implemented in 2011, thousands of lives could have been saved. Okay, so this is a very good example of tsunami earthquake, Java tsunami earthquake. Jim Mori gave me this slide, and there are two pictures. This is the effect of shaking, almost nothing. This flimsy-looking building survived without any sign of damage. However, the tsunami was very extensive. That corresponds to this kind of spectrum. I'm a bit cheating. The spectrum is from Nicaragua earthquake rather than this earthquake. But anyway, at short period, spectrum is deficient. The long period is large. So this is a very typical thing. So macroseismically, this was noticed for a long time. However, only recently, we could really understand in terms of source spectrum. So that's an advancement. Then if we understand source spectrum, we can come up with a way to make better warning, more reliable warning, so that the technology can be effectively used for earthquake hazard mitigation purposes. Okay, and more recently, a lot of tsunami earthquakes were discovered. This is one of the most striking example, a Mentawai earthquake of 2010. And this is a trench. This is Sumatra. And there are some islands in between. But this one event happened really very close to trench, only 10 to 15 kilometers from the trench. Nothing else here. And yet this produced large tsunami, not very large, however, large enough to cause damage. So this is a very typical tsunami earthquake. And if you look at the spectrum, it's deficient. And this is somewhat unusual thing. 1907 Sumatra here. And of course, 1907 seismic observations were not very good. So we don't have very high quality data. However, macroseismic data indicate that there was a tsunami over nearly 1,000 kilometer stretch in the northern part of Sumatra over here. But we didn't quite understand what it was. But recently, we recovered old records, and found that there was magnitude 7.5 to 8 event around here. And however, magnitude 7.5 or 8 event wouldn't produce this much of tsunami. So by inference, we thought this earthquake was very similar to Tohoku earthquake. There was a fairly large event, ordinary event around here that triggered slip near the trench that caused large tsunami. And we knew that before Tohoku earthquake. So in that sense, Tohoku earthquake wasn't really a big surprise. This compares 2011 Tohoku earthquake. And this one, there was a foreshock somewhere around here, which triggered the slip near the trench. And this one is 1907. We don't know much about it, but there was a 7.5 to 8 earthquake slightly inland over here, and presumably that triggered the slip. This is the same scale. So in terms of length of the slip zone or length of the area affected by tsunami, this is actually much bigger than Tohoku. And rather interestingly, if you look at the surface area magnitude of Tohoku earthquake, is only 8.1. So if you have tsunami warning system measuring only surface wave, this event will have been given magnitude 8.7. And of course, they would issue tsunami warning, but it wouldn't be very large. However, the actual MW determined that the long period is 9, so this produced a big tsunami. So they should have monitored using this, but instead, around that time, they were monitoring using this. And that was really a very obvious problem. And, but now I think it's going to be corrected. In case of Sumatra, probably surface area magnitude is only 7.5 to 8, and we don't know how big the long period magnitude was because there was no long period instrument, only tsunami. So this kind of event, everyone said the Tohoku event was very surprising and surprised. However, I don't think it's really that strange. It's one of these tsunami earthquakes that can happen anywhere. So we really have to keep in mind so that we have to have better tsunami warning system so that we can quantify this in a matter of 10 minutes or so. And technology-wise, that's possible, very feasible now. Okay, now there's a very interesting problem. Vara Hiroo-dottir, she's one of our PhD students and went to Mexico to work on subduction zone earthquake. She made this map recently and gave it to me. Well, this is rather surprising. I didn't actually recognize that one. This is Mexico subduction zone. And this is near Jalisco, where magnitude 8 earthquake happened. And then this is Guerrero, 1950s, there was a big earthquake. And the Michoacan earthquake, famous one, happened here. So in a way, we thought Mexican subduction zone has experienced a series of great earthquakes for the last 50 years or so. So in a way, that's a standard subduction zone. But when they really mapped the rupture zone, all these big earthquakes are slightly inland. They didn't break the zone near the trench, where in other places, tsunami earthquakes happen. And Jalisco probably broke here, and over here, you go into Tehuantepec, so we don't know. But anyway, for this long stretch, nothing has happened for the last century. Well, you can have two interpretations. This part may be permanently aseismic. The slip is always completely creep, so you don't have to worry about it in terms of tsunami. The second possibility is this is a place of potential tsunami earthquake. And strain rate can be very slow because a large portion of the slip could be creep. Only small part of the plate motion accumulates as seismic strain. And we don't know yet. And well, there could be some way of telling that by looking at the sediment structure from here to here. And I guess same situation exists for the Ryukyu arc. Ryukyu arc has never really experienced a great earthquake near the trench or domain B, we don't know. But since essentially it's aseismic, but however, this kind of tsunami earthquake may happen on time scales of 1,000, 2,000 years. So we just don't know yet. So So it's important to really try to understand it. And I don't know how to understand it, but certainly geologists can be very helpful, because by looking at the structure of a accretionary prism, it may be possible to see whether a similar event has happened or not. And in terms of tsunami hazard, I think this is a really very serious problem. And even if you improve tsunami warning system, still, if that kind of event happens, it's going to be a big problem. So I think it's critically important question, particularly for Taiwan. Well, let's look at the next intraplate earthquake. Intraplate earthquake here in outer ice or in the deeper part of the subducting slab. This is the place where that aftershock of the Tohoku earthquake happened on April 7, 2011. I showed you a PGA map, and I compared it with the main shock, and say in Sendai around here, this produced even stronger shaking than the main shock. So we will show you a few of them, and we should at least pay attention to that so that we can come up with much better hazard mitigation practice. Well, going back to the same figure, the bottom four are the intraplate events, and in all these cases, spectrum is very enhanced, like this. And this is, again, very large difference, factor of 5 to factor of 10. In this case, at higher frequency, it could be even larger. And these are only for big earthquakes, which we sort of studied one by one. But recently, Lin Ye actually looked at all the events, nearly 100 events, on subduction zone events. And this general pattern holds for almost everything. So this is a very characteristic difference between domain B, A, and intraplate. Okay, again, I want to show you this slide. This is a Tohoku main shock, and of course, I'm sorry. Affected area is very large, but this is a kind of PGA. And this is the aftershock on April 7. Magnitude is only 7.1, and the depth is 50 kilometers. So it's an intraplate event. Going back to this figure that happened somewhere around here. So it's a very different environment. And as you can see, the PGA in Sendai in particular, here, was even bigger than PGA from the main event. So spectrum is very different. So in this case, it's essentially single frequency measurement, but you can see the difference. Okay, another example. This is one of the worst intraplate events in terms of damage. 1939 Chile earthquake that happened essentially in the area of the recent Maori earthquake. And this is a very recent study by Beck and others. And surface wave magnitude was 7.8. And I don't know exactly what the MW was, but not much bigger. And the depth is 80 to 100 kilometers, but the shaking was so strong, apparently, and also the structure wasn't very good, and it had a death toll of more than 28,000 people, 28,000. So in a way, this is the worst event in Chile, despite relatively small magnitude, while Chile has lots of great earthquake with magnitude 9.5 and 8.8 and so on. But this one really dominates in terms of damage. So this illustrates how important it is to study intraplate earthquakes, even if they are relatively rare and relatively small. And this is another example, 2009 Padang earthquake, and 7.6, depth is 78 kilometers, and more than 1,000 people perished. Well, it's a very similar case. And of course, in these cases, perhaps the structure had a problem, not very good. So it's a combined effect of strong shaking and some structural problem. Well, recently, there was an Aleutian Island earthquake, 2014, magnitude 7.9. This is probably the biggest event in this depth range, among the biggest at least. And we looked at some detail of this event. However, in this case, this area usually is pretty good in terms of damage because there are not many big structures. The population density was very low. But globally, if you look at all the events like this one, we do have this kind of thing. And okay, and many of them are subduction zones, and many of them are within the subducting plate. So this type of event is very common. And from hazard point of view, we really have to keep an eye on this one. In particular, in Taiwan, there were two events to consider. One is 1909 event here, and the other one is 1910. And this was given 7.5. This is given 7.6. But these are, I don't know how they determine. This one is somewhat smaller than this one. But anyhow, there were two events very recently in Taiwan. And we sort of want to investigate these events to see what kind of events they are and whether those events can have a serious impact on Taipei. Well, of course, between 1900, when these events happened, and at present day, the situation is entirely different. So 1909, 1910 had some shaking and some damage reports, but of course not very serious. But if the same event happened today, we have to deal with this problem. So for that reason, even if the data are incomplete, it's rather important to really investigate this one. And of course, for 1909 event, many papers have been written. The first one is Kondo, and he wrote a very detailed account of this event. And there are lots of papers. So to some extent, this event was very well understood. But recently, we wrote a paper by looking at some old records from several stations in the world, well, mainly from Japan, because 1909 events this size, we don't have many good records. Anyway, the conclusion is this event, as was already known in these studies, is very close to Taipei, right underneath, and then presumably related to the subducting Philippine Sea Plate. Although if you look at the cross-section, it seems to be off slightly, but we don't know exactly how to define plate or anything. The fact is, it's somewhere around here, right underneath Taipei, and the magnitude is probably around 7, and depth is a bit uncertain, but between 50 and 100 kilometers. So this is really very similar to these events and similar to these events. And since they were very damaging, we need to understand how damaging this event can be. All right. So this is the seismological aspect of 1909. So I want to compare this with some ground motion produced by more recent event of the same type. The earthquake I'm comparing with is Geio, Japan earthquake. Magnitude was 6.8, and depth is about 47. It's very similar to this 1909, slightly smaller maybe. And it happened right underneath here. And this is the PGA map. And the response spectrum, acceleration spectrum, looks like this one, two horizontal components. And this wasn't really that damaging. In terms of total damage, it wasn't very serious. But a friend of mine, Professor Dapen Zhao, was at Ehime University, and he was in his office, and apparently his scientific material all fell down, so at least it was very damaging to him. And for ordinary houses, it wasn't that bad. However, shaking was very strong. So if it's slightly bigger, it could have been far more serious. Well, anyhow, the more quantitative comparison can be made. Acceleration spectrum spectral acceleration, I should have said, is like this one. And this is spectral velocity. I don't know where you can read the number. This is about 1g. And this is approximately 80 or 50 to 70 centimeter per second, which are very respectable ground motion because as this is interpolate, so high frequency is very strong for the given magnitude. So just for a matter of comparison, I put spectral acceleration and spectral velocity of CWB Tainan station for the recent event. Mainon, it's okay, earthquake. And the same scale. So amplitude, you can compare this one to this one. And this period is about 1 second, 10 seconds, and so on. All right, this is velocity. So if you look at this one, in terms of spectral acceleration, this interpolated event is much bigger. This is very close to the epicenter. And so at least this could be larger in terms of effect than this earthquake. And that's a kind of calibration regarding how to assess the seriousness of this kind of event. So if this was serious enough, this would be even more serious. And in terms of velocity, it's very comparable. So this kind of event, even if the magnitude is relatively small, it's really not negligible. And depending upon what kind of structures you have, or also type A basin structure, this 1909 type event can be very serious. So at least it will be useful to look at or existing old structures in type A to see how the event with this kind of spectrum can affect those buildings. That's a pretty useful thing to do from completely layman's point of view. Another comparison, I already showed you this April 7 event, aftershock of 2011 Tohoku earthquake, and I said it has a very strong shaking. So instead of just PGA, to make it more quantitatively, I computed the spectral acceleration and spectral velocity in the same way as I did for the previous event. And the black curve here is for this event. And this red one is Mainon at Tainan Station, east component. So in this case, it's almost a factor of 4 to 5 larger. And the same thing for velocity too, spectral velocity. So I'm not really, I have no expertise in engineering, but at least this is observation. And you know probably what happened in Tainan from this kind of ground motion. So you can probably extrapolate what will happen in type A if we have this kind of a ground motion. And this did happen in 1909 and can happen in the future, even stronger. So at least this type of interpolated event, we really shouldn't ignore in any hazard program. Of course, we tend to only look at shallow events because they are more damaging in general. But the interpolated events occasionally can be very damaging. One more example. Well, this is kind of my favorite now. This is 1910 event. This is north of Taiwan. And of course, this must have been known among Taiwan seismologists very well. There is a very nice record from Gellingen, Germany, a 3-component. I'm showing only east-west component here. This is a wonderful record written in 1910. And this is a P wave, and these are the depth phases for P wave, PP and SP. And this is SKS, and this is SS and PS, the surface reflection of S wave. All right, it's a very good record. And of course, there are other records in Japan, and maybe you have. Well, we did some experiment. This is a good-looking old records. Now, we have modern technology computing waveforms for lots of structures. What can we do if we have only single 3-component record? To what extent we can determine this one? Well, we can now compute waveforms for thousands of models very quickly. Actually, I don't even compute myself. We make requests to Iris. They compute them and send them back to me in a matter of a few seconds. So basically, I went over the entire, actually Luis did, went over the entire sort of model space, slip angle, rake, dip, and strike, and compute waveforms. What did we look at? Well, the amplitude ratio first. So we looked at the amplitude ratio of P reflection, S, and so on. So only up to here, and then picked the right combination which would produce the right waveform. So as you can see, this is the same record as this one, polarity flip. And this is the one computed for this mechanism. And then we can determine mechanism, MW, which is 7.3, and the depth is about 180 kilometer, and the location we can determine very well, but it's probably around here. And if you look at this mechanism, it's very interesting. This is a paper from Gao Shenma, 1988, and there are many events, and the mechanisms are determined. There are two events, W2, W3 over here. They are very similar to this one. And these two events are here, all right, slightly shallower, but this is a bit deeper, and the type A is here, so it's really within the plate. So now I think we can understand what this event is. This is again intraplate event in the subducting Philippine Sea plate, and which has a very strong high frequency, and the magnitude is 7.3 in terms of MW. Okay, so what this event will do, I haven't done it yet, but this is much bigger than 1909, and also you need to think about it. But this is a rather interesting experiment because we do have all the events which you want to know, but we do not have good records anymore. All the seismograms have been thrown out for some reason. So it's really tragic thing because they spent enormous time and efforts to get good recording of seismograms and kept for 100 years without doing anything. And when we want to use them, they have been all thrown out. But fortunately, this kind of record still exists, very small number of good records. Then we need to use our modern technology, just use a computer to compute lots of waveforms to pick up the right one. I think this is a kind of rather interesting approach for studying old records. So at least these are two intraplate events near type A. And I'm not saying that these events would happen. What I want to emphasize here, the subducting Philippine Sea plate is capable of generating this kind of event. And the next event may be even bigger or smaller, but at least in the past, the plate produced this kind of event. And it will probably produce a similar kind of events in the future. So we really have to look at this one. So this is again where modern seismology and engineering can work together and help. You can assess the importance of this kind of event in the city of Taipei, particularly for old structures, very poorly constructed old structure. Well, now to deviate just a little bit, lots of strange things happened in this business. And since I am not an engineer and my expertise is very limited, so from here on, it's more like a layperson's view of what happened. But to me, this is really unbelievably strange, but I think it's important, and this should be really looked at more seriously by engineers. Well, I said some events are really big, and like great earthquake, magnitude 9 or larger, and this is a spectrum of those events, 2004 Sumatra, 2010 Chile, and 2011 Tohoku. All of them are very large at long period, but high frequency, say 5 seconds or shorter here, it's kind of scatter. And if people look at the log scale, log plot, like this one, Well, it's kind of messy and scattered, didn't pay much attention to the difference. However, if you look at it carefully, great earthquakes, this group, and the large earthquake, this magnitude 8 Tokachi-oki earthquake, there is a significant difference, and a factor of 5 very sometimes. So in seismology, factor of 5, you take log scale, it's not a big deal. However, for engineering, factor of 5 is a big factor. So we are really curious about what this factor of 5 would do in terms of large buildings. Okay, and this is one first amazing thing to me. Maybe it's not amazing. Well, I'm sure this is amazing, but they didn't say it's amazing. Well, there used to be a building in Osaka Bay, Sakishima building. This is a 52-story, 256-meter. It's quite impressive like this one. And this is about 800 kilometers from the epicenter of 2011 earthquake. Now, of course, 2011 is magnitude 9. And then on the top, the roof, it shook 1.37 meter, just the regular amplitude. So both ways, it's about 2.7 meter this way, and 10 minutes. This is a time scale here, 0 to 10 minutes. So I don't know how people felt when the whole thing started shaking. 3 minutes full amplitude, 3 meter full amplitude for 10 minutes. It must have been very scary. And of course, the building itself was intact. However, internally, elevator shaft and lots of secondary structures were damaged. So for the time being, they couldn't use it. But that's okay. But the question is, of course, this is completely from outsider's view. Should we really keep using this building? Well, they decided to use it. And the people went back. Now this is occupied. Well, it's a bit scary, actually. Okay, why it's so scary? This displacement at the base is 9 centimeter. And this is already very large, considering that this is 800 kilometers away. Okay. And then what happened is this. This is a record in Sendai from the 2011 event. And this is the real common scale, the same scale. So it's a very impulsive, good-looking record. And then, after having propagated nearly 800 kilometers to Osaka, this red curve here is the basement, the downhole, some depths below the building. So the amplitude decayed from Sendai to Osaka by this much, nearly factor of 30. This is more or less quite reasonable. The wave propagates from Sendai to Osaka. It was decayed by factor of 30. However, this dark trace here is the ground motion right above on the surface. So it was multiplied by factor of 30 from 2 kilometers to the surface. So if you compare this amplitude with the amplitude in Sendai, it's about the same. So no attenuation from Sendai to Osaka. Even worse, this is more impulsive. Now this becomes pretty much harmonic. So duration is not 10 minutes, but this is the motion fed into the building at the base. And the building started shaking, and the roof moved by 1.37 meter. Well, why did it happen? And I don't think people designed this building anticipated this kind of thing to happen from magnitude 9 earthquake at 800 kilometers. So they should have been surprised, but they never said they were surprised. It's very unusual, and I don't quite understand. And I asked lots of engineers, and of course, common answer is, wow, this is a combination of seismic source, pulse effect, and site response. Of course, it didn't happen. However, exactly how it happened, we should really investigate in great deal to understand how it happened, why it happened, because there are many buildings like this one, and if it happened to here, other places, same thing may happen. Professor Iwata's group at the Kyoto University has been doing very good work, and their group seems to have solved up to 70% of the problem. So it's a combination of special mechanism and path effect to Osaka Basin, and of course, there is a big site response. So that combination resulted in this rather surprising observation. So, well, I thought this is a good example that big surprise can happen, so we have to prepare for that. This is a schematic figure. Again, I'm just repeating this one. This is epicenter, and this is 2 kilometers beneath Osaka, and the amplitude decayed by a factor of 30. And from 2 kilometers to the surface, it was amplified by a factor of 30. And then it was amplified by a factor of 14 from bottom to the roof. So from here to here, it's nearly 500 times. So no wonder why the roof shook that much. So, but this did happen, and if it did happen once, it can happen again. The question is, under what circumstances this can happen? Okay, so importance of site response, directivity, we have lots of surprises. And of course, the first surprise was probably this Mexico City experience in 1985. Of course, Mexico City is built on a very soft lake bed, so in a way, it may not be surprising, but the observation, a very good observation at the SCT side, it's about 2 seconds, and the spectral acceleration is nearly 70% of G, and then CAO site here, it's a bit longer period, and 30% of G. And this was really big, and it was really surprising at the time. This is, I don't know to what extent this particular motion was responsible for this building, because there are 3 buildings of the same design, and one of them collapsed, the other 2 survived. So there could be, again, some combination of ground motion and the structure and everything. But that's true, probably. But we have to realize that this is the real world. We are not living in a perfect world. We have sort of deficient structures, and we have very bad combination of site response, path effect, earthquake, and this can happen. We are living in this kind of world, so we can't really just say, well, this is just by coincidence. And then this Kathmandu earthquake happened, and of course, I have no knowledge regarding how to interpret this one, but I can still read the scale. This is a ground motion acceleration, and this is an acceleration response spectrum here, and this is displacement response spectrum. And the acceleration response spectrum, this is nearly half G at a very long period, nearly 4.5 seconds. I'm sure you know these things. And this strong peak is surprising. This is even bigger than what was observed in Mexico City. And also, another surprising thing is this is spectral displacement, and it's nearly 3 meters. And I have been told by many people that now this seismic isolation, base isolation system has been very successful in the past, and looks so, and that's a great accomplishment. However, usually the allowance is only 1 meter or so, even large ones. So if the ground motion displacement exceeds 3 meters or something, it may hit the side, and that can be probably very serious, but I don't know. I really want to know the answer. If this motion goes underneath a base isolated building, would it be okay, or would it not be okay? But I don't know. I really haven't had a clear answer to that. Okay, so just to compare, I'm using the same scale, both time scale and amplitude. This is in Mexico, and we were surprised at that time with this big peak and long period peak here. But the Kathmandu record is much bigger at this period, about 4 seconds. And this is the ground motion beneath Sakishima, and this is responsible for shaking of 1.37 meter on the roof. But if this happened to the building, it will be really much more serious. And to show that, this is the illustration. This is the same figure, and the roof of this building shook 1.37 meter like this one for the displacement of 9 centimeter. However, in case of the Kathmandu record, it's 170 centimeter instead of 9. So you compare this one with this one, 10 times bigger. So simple question from a layperson would be, if this is what happened, 9 centimeter to here, if you multiply this by factor of 10, what will happen? Well, it will shake by more than 10 meters, and whether the building will be okay or not, I don't know. Well, but they still think that it's okay, and this building is now being occupied. Well, the problem is, this building is next to the Nankai earthquake, which people think can be magnitude 9, just next to it. So that combination, I'm not sure whether it's really by common sense it's reasonable or not to have this kind of building next to potentially magnitude 9 earthquake. This is a sort of common sense kind of question, and both seismologists and engineers should really think about. I don't have a real answer myself. Okay. Well, so this is one of the things which happened rather unexpectedly. And then recently, Professor Ma sent me this Taiwan W21B record. And this event happened Friday afternoon over there, and before seismology seminar. So I quickly looked at the NEIC, and the NEIC these days do very well. And I had all the technical information at hand. And fortunately, when I was looking at ordinary TV, they said there wasn't any report of damage or anything, so I thought that was good. Then after the seminar, apparently it was pretty bad. And also, we saw this pulse. It's a spectacular pulse. The scale is about 1 meter. Okay, this is this is velocity, right? Okay. This is azimuth displacement, okay. But it's only for that azimuth we have this large pulse. And of course, I know nothing about the local structure, mechanism, or any detail. But this really reminded me of important pulses of this kind. So in the context of large pulses in seismology, this is it. Well, this is a collection of ground motion velocity pulse from very famous large earthquakes. Of course, in 1940 in Pearl Valley, El Centro, this was really the basis of many engineering study many years ago. You really don't even see it, but there could be some motion. And Kobe earthquake of 1905, this pulse became very famous, and it's about the same size. And the North Ridge, this is also pretty spectacular here and here. And this two sites. And Superstition Hills. And of course, this famous one for number 68 station during the Chichi earthquake. Well, I put this Tainan record here. This is from W21B, not from Tainan station. There's a velocity pulse. If you compare this with North Ridge, it's really very similar if you flip the polarity. And we know how bad this pulse was. Some of the damage was caused by this pulse. And the rather surprising thing about this thing is North Ridge is slightly bigger than this event. And the source duration, the rupture duration, is more like order of 10 seconds. So things happened over 10 seconds. However, if you look at this pulse, it's only 1 second. So how come the 10-second motion became 1 second motion? There must have been some mechanism. The standard mechanism is directivity. In principle, if the rupture propagation toward the site is the same as S-wave speed, you have impulse. So it's possible to have this, and that was probably the interpretation of this one. But for other events, the same thing happened, like Superstition Hills and Kobe. So one really general conclusion is, regardless of details, if we have magnitude 6.5 to 7 event, the source duration is 10 seconds. However, in certain directions, you have very concentrated energy because of directivity. So this directivity became very important. So I was really quite intrigued by this one. Well, how come this one became so narrow? Because the source I know is more like 5-second to 10-second duration, but this is really 1 second. So I don't know really the mechanism, but at least regardless of what happened, time and amplitude is about half this one. However, still comparable to this one. So there could have been some problem with the building themselves, but still there was a fairly substantial ground motion. Again, the combination of mechanism, site response, a 3D effect, and everything. So these things can happen. Well, to get into a bit more detail, I was really curious about where that pulse came from. And I really like to, this is my personal taste, I really like to look at the displacement waveform first over broadband so that I can see both near field and the far field. Because if you look at only far field, it's a kind of sequence of pulses, and it's hard to identify, understand exactly what we are looking at. Well, the top ones are observations. This is a PRRT record, W21B displacement. It's very impressive. I mean, this is a double integration with some filter, but essentially, it's there. It's a near field and a far field, regardless of where this came from. And this is a east-west component, this is north-south, this is vertical, or the same scale. So vertical is very small, and presumably incidence angle is very, very steep. And this is Tainan 1 station, and very similar as far as east-west component. I think amplitude is smaller here. And there is some similarity on this north-south and also vertical component. So it's really observation is a wonderful, really reliable observation. And then I sort of generated synthetic record using point source and some layered structure, more or less appropriate for this region, although I knew nothing about it, so it's pretty much arbitrary. No, we can produce this one. This is a computed one. This is a near field and the far field S-pulse, SV mainly, and this is a north-south, this is vertical. So the first order, the shape is very similar to this one. So common sense is, without knowing anything, I think these pulses are produced by the source. However, if you really look at the pulse width, this is very narrow compared with this one. Of course, because this one is computed for very narrow source pulse, only half a second. All right. But the actual source lasted for nearly 5 to 10 seconds. But this synthetic, I just computed Green's function by using very narrow pulse. So, and this is a velocity pulse, synthetic. This is W21B velocity, and it's pretty same size. So what we can learn from here, at least I learned from here, is no matter what, there was some mechanism between the source to the station that made it very narrow. The source duration, no question, 5 to 10 seconds. But somehow it became very narrow. If I make it 1 second, you can't produce this one. So it has to be 1 second or narrower. Well, of course, one obvious explanation would be directivity towards this station. But just by standard slip inversion, resolution isn't good enough. Well, it's an indication that there is a directivity towards northwest, but not quite. So that's where I am. And I'm very anxious to, when I came here, I was very anxious to know exactly what's being found here. And of course, there are other possibilities. This pulse came from somewhere else. That's certainly possible. But the similarity of displacement record is quite striking to me. And this is another big surprise of this kind of thing. So we have to always live with this kind of big surprise in seismology because directivity, 3D structure, basis structure can always combine themselves to produce something very strong. Okay, well, the third one is recognition and understanding of outliers. and why we have this outliers physics and the interaction. And of course, this is also a kind of outlier, but if you look at the SH pulse, it's not really quite outlier. It's very common to this type of earthquake. Okay, and so we need to understand what the average earthquake is and what the outliers. So average earthquakes can be defined as such events that follow some standard scaling relation. And that average can be used as a scenario earthquake for the future. And that's a very good practice. And I'm glad that now Japanese government is really trying to do a lot of scenario earthquake study on the basis of seismological results. That's where science is very effectively used. However, as I said, average is average. And in natural process, we often see outliers. And first, we want to know what average is and what outliers are. Well, and of course, to define average, as I said, we need some scaling relation. There have been many, many scaling relations: fault area, magnitude, stress slope, and all kinds of things. But one very robust scaling relation, which can be determined from a long period analysis of seismic waves, those parameters are seismic moment, M0, and the source duration. We usually use twice centroid time T sub C. And this relationship is very stable because we don't deal with space, only time. And seismology works very well as long as we only look at time instead of spatial parameter. And this is one example. This is a bit strange plot. It's not quite scientific. It's mainly for a lay person. Horizontal axis is time since 1990 to 2012. And this one is this estimated observed centroid time minus estimated centroid time. And that estimate is made by the scaling relation. TC, half the source duration, more or less, is proportional to cube root of seismic moment. And for many events, this works really very well. However, sometimes source is not quite symmetric, so this may not be quite to TC. And also for small events in this kind of plot, everything will be in this cloud. So this is not quite scientific, but at least to show which events are outliers, which events are normal. This is very useful. And for example, if we use this scaling relation for 2011 Tohoku earthquake, magnitude 9, you would expect 73 seconds for T sub C. And the observed one was 80 seconds. So it's very close. And this is what Yenyu has been looking at. It's quite a very small earthquake. This scaling relation is established for events bigger than 6.5 or so. Well, why don't we go down to a very small event to see how it works? This is magnitude 1.5. Well, observed TC would be about 15 milliseconds, and the scaling relation predicts 60 milliseconds, very well. So this is determined for magnitude 9 all the way 1.5. And then for main one, it's 4.3 seconds, but 3.4 seconds. So it's pretty normal here. So all these events are more or less average events. However, if you look at that one, 2004 Sumatra earthquake is very different. And the 2006 Java earthquake, which is tsunami earthquake I showed you, is very anomalous because it ruptured over a long fault. And Tohoku earthquake, for example, is on the other side. Even if this has tsunami earthquake element, it went the other way. The reason is the stress change in that trench slip zone was so high, so by combination that it went negative. So this deviation can be interpreted in terms of physics of the source. So if you include this one, we can use this relation to define the average behavior and the range of variations. And this is very useful for considering scenario earthquake. If you want to have scenario earthquake, first you want to understand what the average sort of character would be. At the same time, you want to know what the range, possible range would be. And that's why I thought this may be useful. So the scaling relation gives the average, and the outliers give the range. And the problem here is outliers often tend to be most, what happened? Most disastrous, like Sumatra earthquake or Java event, and in old days, 1896 Sanriku earthquake. So it's really important to understand why we have outliers, and now we have some physical explanation why it can happen. Okay. So this is the kind of scenario earthquake Japanese government came up with for the next Nankaido earthquake. Overall character is derived from the total length. However, they now know that the slip can extend to the trench, so they added something, and also it can go to deeper, so they modified it. So they considered both average and the possible range inferred from outliers. They came up with magnitude 9 and estimated all other parameters like possible tsunami inundation and so on. Problem is, as I said, that the Osaka building is sitting right here. That 1.27 meter oscillation happened for event 800 kilometers away over here. So the question is, what will happen if this happens? That's a bit scary kind of thing. And I really want to know some answers from engineers on this. Okay, so finally, no matter what we do, we understand lots of things in terms of physics and with technology, we can understand lots of things. However, still, the event will happen all of a sudden. Then we really have to deal with it. And the only way, as far as I can see, is to develop some early warning system for tsunami and earthquakes. And this is really critically important. For tsunami warning system is much easier because we have much longer time to worry about. But the earthquake early warning is very difficult. But I just want to discuss a few things because here it's like it's a kingdom of early warning system here in Taiwan. So you have real experience, you have lots of systems. So I don't really have to say too much about it. Well, first tsunami warning. So as I said, it's very important to characterize the event very quickly, not only the long period spectral amplitude and also the mechanism, because strike slip events don't produce tsunami. So if the event is strike slip, even if long period amplitude is big, you shouldn't send warning. So it's very important to determine both. Now, modern broadband seismology and GPS can contain the complete source information in the first few minutes. So for this purpose alone, we have good record, but we don't need everything. Just to cut off for 10 minutes, and the rest we can throw out. Only for the first 10 minutes are critically important. And the rapid, less than a few minutes identification of tsunami source is now feasible. It's really feasible. Effective implementation and education are what are needed. So fortunately, I think everything is moving in that direction. Every country is doing it. And so hopefully, as far as tsunami warning is concerned, it will be very effective and we can save really lots of lives due to tsunami. Only problem is you cannot save properties. So if we have a big tsunami, we can save lives, but we cannot save properties. So the government has to come up with some way to compensate that. Well, this is the illustration. For 2011 Tohoku earthquake, event happened here. And as everyone knows now, the seismic source moment rate function lasted only 150 seconds or so. So really, everything was over in 2 minutes and a half. And this whole information is contained in a waveform like this one, only in the beginning. You don't need anything after this. Then you can determine magnitude and size. Now we have high-rate GPS all over, so you can use it, same thing. So you can have much more detailed analysis. Well, and fortunately, NAIC went to much further than GMA. And even at the time of 2011 earthquake, they were running this real time. And just to make it short, at 20 minutes after the origin time, they came up with magnitude 9 and came up with this mechanism. So these two, 9 and the mechanism, were sufficient to really issue reliable warning. Unfortunately, there are two problems. One is 20 minutes. 20 minutes is quick enough, but still too late. The reason why it took 20 minutes is the Japanese data didn't go to NAIC. So NAIC had to wait until seismic waves arrive at European stations or US stations or other places. So if Japanese data were sent to NAIC at the time, it could have been done in 5 minutes. It's really a matter of technology, and it's available. So we don't have to really, we can just improve it. Oh, I should have used the microphone, I guess. And some case history, this I found very interesting. September 16, 2015, Irapero, Chile earthquake. This happened at the time of the meeting in Mexico for the Michoacan earthquake. And this happened the day before, actually. And Professor Madariaga was there at the meeting, and he has very close contact with the Chilean colleagues. So he was getting almost real-time information from Chile. And it was quite impressive because this event happened in the seismic gap defined by 1940s Irapel, same place. So in a way, they have been waiting for this kind of event. And then this event happened. And this is what happened. This is communicated by Sebastian. He was doing PhD, and I corresponded with him a few years ago, but I haven't even met him. He is very ambitious. He is very good. He takes action. So he actually was doing real-time thing. And the Chilean National Seismological Center actually determined this mechanism and size in 5 minutes after the origin time. So they knew everything at 5 minutes after the origin time. But that alone isn't very useful. Then he sent this information, or maybe he didn't. It's automatically transmitted to the Navy Hydrographic Service in charge of tsunami alert. And then Emergency Office of the Interior deployed an evacuation plan for the coastal population. So they really evacuated the people very, very quickly. And what happened is, well, this is how it worked. Of course, the instrument went off scale. And some people complained that the modern instrument goes off scale when big earthquake happens. Of course, it goes off scale if you wait long enough. But you can do everything before it goes off scale, because I said you need only 2.5 minutes to understand everything. Then instrument will go off scale after 2 minutes, but we don't care. So this is apparently what they used, all the Chilean stations. And then they could determine it in a matter of 5 seconds or so, and to the first order, it was correct. Well, and then the question is why Chile's latest big earthquake has a smaller death toll. Firstly, the latest earthquake was not as powerful, so there wasn't much tsunami. However, regardless of whether there was really tsunami or not, it's important to know the system worked in real time. So if the tsunami was really big, it must have saved a lot of lives. So, of course, training and everything. Of course, the experience with Maui earthquake must have been very important. So everything worked very well, and they are very proud of it. And Madariaga said, well, this may be the first time that the seismologists who are quite became very popular among the public in the epicenter area. Usually, whenever we have a big earthquake, seismologists are not one of those people who are very respected. So, but this is really rare case in which they had a very good reputation. Earthquake early warning. Of course, I really don't have to anything because you probably know much better than I do. Many systems are working, like P-Alert, Japan, and Mexico. And most important is warning at the ground zero near the hypocentral area. So that has to be done in a matter of a few seconds. And the automated system is necessary. I don't really know the situation here, but the seismology part of early warning is essentially 80% done. I think everything is working and information is released. The question is how to use that information for practical purposes. And to some extent, it's an engineering problem. So again, this is where coordination of engineers and the seismologists would be very important. And the good thing is like this. Well, this is one of the things, of course, you know, and to get not only warning, to get this kind of map immediately is extremely important. I mean, no matter how we do it, damage would happen, and it's really important to know the distribution. So technically, I really think it's done. So next thing is really to make good use of it, and it's really quite an accomplishment. And the California, Rob Clayton and others have been working on the same kind of concept. But I think their objective is not necessarily early warning. They want to know the building response and other detailed seismic image. But anyhow, this is going to be very useful. And of course, as you know, in case of bullet train, it's a centrally controlled system. So they could use rapid information for automatic control. In this case, 24 trains were running, and they could shut down the power, and apparently they could apply emergency brakes, and all trains stopped without derailment. And this is an interesting case. There was a Japanese company, Oki. They really wanted to protect their delicate machinery because in 2003, they sustained $30 million loss because of the damage to the equipment. So they made their own on-site warning system, and it worked very well in 2005, and apparently also worked very well in 2011. So this is a really good use of early warning system. And in this case, certain engineers are involved. They picked up warning concepts developed by seismologists and implemented it for their system. And I think this direction is really very promising. Okay, I probably have to skip this one. This is the kind of concept of on-site warning. We just monitor vertical motion like this, and the biggest motion will happen on horizontal components, so you can monitor it. And if you have basically big motion on vertical component, you can make some threshold warning for horizontal amplitude. However, the problem is if you plot everything together, this is one of the fairly complete database for all the Japanese earthquake. There is a scatter. Again, this is the problem of dealing with natural process. You can't have deterministic relationship. So horizontal axis is the amplitude of the beginning, and the vertical axis is a PGV. So idea is to predict PGV from the vertical component. But if all the points are on the straight line, you can do a perfect job. However, this is the real world. I don't think we can improve this one because this is really what happened. So what this means is, in addition to successful alarm, we have some missed alarm. In this case, even if ground motion eventually became very big, the initial motion was small, so you missed them. In this case, you issued warning, but the ultimate ground motion wasn't very big. These are false alarms, and these are successful no alarm. So in a way, we have to deal with this one, this one. So what is really important, maybe this has been already, let's skip this. So we need to develop updating mechanism. So when we have missed alarm, well, we have to have some way to update information so that we can reduce missed alarm. Or if you know that alarm was false alarm, then you want to cancel it as quickly as possible. So reduce the impact of false alarms. And also, we have to come up with a way to use information for automated control system. And all of them are being sort of done. One of Tom Heaton's students had recently an interesting thesis to deal with this one. So things are moving in that direction. But I think we can move more quickly. Well, this student is engineering. So in a way, Caltech, there is some collaboration between seismology and engineering is going on. But I think it's really to make good, effective use of early warning system. This collaboration is a key. Okay, so this is okay. So just to conclude everything I said, maybe many of them are obvious to you, but the earthquake process has deterministic and non-deterministic elements. And we cannot get rid of non-deterministic elements because this is really natural process. So where deterministic element dominates, we can make some forecasts, but still with large uncertainty. But it's very important to be able to understand what's going on. And that's a difference between now and 50 years ago. 50 years ago, we really, empirically, we made some forecast on the basis of a seismic gap, which was a great accomplishment. But at least now we know much better than what's going on, strain rate and that sort of thing. Number three is large uncertainties are inevitable because of non-deterministic elements, and outliers are inevitable. And detailed modeling of individual earthquakes is important to define scenario earthquakes and other outliers. And individual earthquake study is just so important in a way. This is the basis of seismology. And unfortunately, very often, many important earthquakes, and lots of studies were made, but many of them were not published. People did a lot of study, but only a small portion of that was published. And if you submit a paper on the same earthquake over again, some editors would say, well, this has been already published, nothing is new. But this nothing is new is a very important thing. If the second paper had nothing new, that means the first paper must be fairly correct. So nothing new paper is very important, but some editors don't understand that. This is a slightly different science from ordinary physics or chemistry, where experiment is done. So we have to change that mentality. I think for documenting individual earthquake, nothing new paper is one of the more important contributions so that we can really establish the fact. We can't verify by experiment or by going to underground, but if you have 10 papers, nothing new, usually we can establish the fact. So that's really a different science in a way. And diversity needs to be considered for effective hazard mitigation strategy because the earthquakes are so different. So we have to use different strategy for different events. And to cope with unpredictable nature of earthquakes, effective real-time systems need to be developed, and they have been developed, but we have to develop the way to use it. So, after all, however, we should live wisely without unduly worrying about the hazard, because we can't avoid it no matter how. But the good thing now is with modern technology, we can really use that technology for practical purposes to mitigate the impact of earthquake. So using the best of our knowledge and technology to minimize the impact of earthquakes. And that's really very important. And to do that, we need to have good collaboration between engineers and seismologists. Thank you very much.
Very nice talk. Any question or comments? Okay, maybe I have one question talk about ground shaking. So for the tsunami earthquake, is slow shaking. Intraplate earthquake is high shaking. It's due to the coupling of the fault plane. Is a major reason.
Well, let's see. Do we need to use microphone? We don't know yet. However, in case of tsunami earthquake, probably a large portion of the strain energy is dissipated in deforming the medium surrounding the source. That means less energy is radiated, large portion of energy. So not only stress drop may not be that different because you have large displacement. The static stress drop will be different. But the total amount of energy radiated is much less. That's why. So I think there are lots of combinations.
I have another question is to talk about the deeper earthquake rise so high shaking. Is only due to the source effect or intraplate, the attenuation structure also
well, in case
produced?
Of that Miyagi-Oki event is a slab effect. The waves come through high-Q slab. So the Sendai was affected very strongly. And probably the 1939 Chile earthquake, the same thing. And Ryukyu case, I don't know, but presumably Ryukyu slab subducts to the north. So we have in-slab event. So
Yeah.
go to Taipei, it's in-slab path, I think.
Okay.
So it's related to attenuation.
Hi?
It's related to attenuation structure.
It does very low attenuation.
Yeah. So any other questions or comments? How about the engineering, earthquake engineering? Talk about the building, 1.3 meter shaking.
Maybe it's very well understood. I don't understand.
Yeah, I also curious about it. They have the 1.3 was shaking, meter shaking. You will cause any damage to the building? Okay, in case no question, I would like to close the section. So thanks, Professor Kanamori again.
Pardon?
Mega source was from zone A, right?
A?
You have the domain A,
Yeah,
B, and C.
yeah.
But mega source is considered to be the domain A.
Which one?
Whatever, anyone. Tohoku.
Talk is A and B. Mainly A, however.
Because I feel over Taiwan 1920, I think it's in B. Yeah, but I feel it's from C to B.
Well,
Not yet rupture to the A. I
but
always also feel
you know,
like
if boundary is very wide, like Chile and Alaska, like Chile is very narrow, Japan is very broad, then you can separate it very well. Like Chile, it's so narrow, it's only 75 kilometers total width. So A and B may not be really quite separated.
yeah. Oh, you want to take a picture?
Okay, sure. I think that's okay. I think I have.
My name is Sura. Can I get contact information via?
Yeah.
I have some question about earthquake triggering or individual fluctuation. So can I get your name card or email?
I don't.
This one?
No,
And
I
My
don't
card.
think. Yeah, I don't think you have your name card because everyone knows you.
okay. maybe I can.
No need.
No, I can.
You do have name card.
I may have. Well, this is the reward. I think this is still okay. So I can contact you. Yeah, email is still okay. I have.
Yeah, I know what I feel for name card.
I don't know.
20 years ago.